Hi there, Matt from Shields Lab here. Um, about 5 seconds ago, I got a tweet from the governor saying that schools in Virginia, and that's where I live, are closed for the rest of the year. So I better make a few more of these videos or I'm going to go crazy. So let's get started. In fact, before we get started, I should probably make a very important point about the kind of learning I'm going to be doing at home with my actual high school students and with my actual kids at home. And it's a type of learning and teaching that I've been kind of figuring out over the last 6 or 7 years as an educator, and that is it's way more fun as a teacher and it's way more engaging as a student for the teacher to kind of step off the stage as the expert. And if you are home right now trying to figure out what to do with your kids, I hope you can find that a little bit freeing, that your job is not to become the expert. So, for example, today we're going to talk about rainbows. And when I started teaching physics, I don't know, 15 or 20 years ago, and the day I was going to introduce the topic of rainbows, I was up all night the night before becoming an expert in rainbows and memorizing Wikipedia pages. And what if Lizzie asked me what the frequency of green light is? And I've got to have that memorized. And I need to come across as a complete expert. That is exhausting as a teacher, and it's just not really real. And so it's much more fun just to sit down and rather than didactic style learning where I stand up and say, all right, I'm going to now tell you everything I know about rainbows. Sit down with your students or your kids and say, hey, I think rainbows are kind of cool. Let's investigate them. And so that's what I did with my kids the other day. It's been a while since I taught about rainbows, so I don't remember everything. So I just kind of sat down and asked them what they know about rainbows and what they think about rainbows. And we kind of went through an exploration rather than, hey, my 4-year-old, why don't you sit down and listen to me talk about rainbows for 45 minutes? That probably just wasn't going to work. So here's where we started. We woke up the other morning and I said, why don't we study rainbows? And the first thing we did is I had my kids draw rainbows. I think that's interesting from an educational standpoint. You might call that the pre-assessment to see what they think about rainbows. Turns out most kids at some very young age pick up the sequence, Roy G. Biv, red, orange, yellow, green, blue, purple, violet. So my kids drew these arcs of color with crayons, and they had the right order. I think one of my kids had red on top, the other one had red on the bottom. So that was something we decided we would try to investigate if that even matters. Also, once again, there was an appropriate "They Might Be Giant" song, so we listened to the Roy G. Biv song. Um, so then after my kids drew the rainbows, then we talked about where do rainbows come from? Why are they always in that Roy G. Biv kind of pattern? And so we talked about how the next thing we did was we did a scavenger hunt around the house. Like, have you ever seen any rainbows around the house? Are there any objects in the house that tend to create rainbows? And um, I think my kids are normal in that they already had a couple of ideas. If you live in a house with windows, you've probably seen a rainbow bounce around your house every now and then. Any kind of beveled edge of a mirror or like a glass table sometimes will create rainbows. We have these little crystal orbs hanging, kind of faceted crystal orbs hanging in a couple places in our house. Those create rainbows. So we went around the house and found places where we see rainbows. And then that led to a discussion of where they come from. And so then from there, I kind of this was me leading a little bit of the discussion, saying, okay, so what color is the sun? And they said yellow. And I think we talked about whether it's yellow or orange or white. And then we talked about why the sky is blue. And, I could have gotten really deep into it, but basically we just said, okay, so most of the light we're familiar with, especially when light comes through the windows and makes rainbows in the house, that's coming from the sun, which is like yellow or white or something like that. And then I talked about that not until recently, maybe 150 years ago, humans actually didn't know what made rainbows and what even light was. And so it was some experiments from people kind of like us, kind of looking at the world around them, going, why does that make a rainbow? Why does that not make a rainbow? Why is red always on the left or something like that? And so what we did is we conducted some experiments. We let sunlight come through the house, come through the window, and we took objects that we thought might make rainbows, and we were able to make rainbows on the walls or on white pieces of paper and things like that. So then I let my kids know that really what's going on, it's called dispersion. I always like to throw in some vocab, and that just means that the white light is getting dispersed. And so white light is actually not really a thing. It's a collection of all the different colors of the rainbow that the human eye or the human brain perceives as white. And we've got things like prisms and glass that can disperse light into its various colors. And what happens is when light travels from one medium into another, the light bends. And the red light doesn't bend as much as the orange, which doesn't bend as much as the yellow, and etc. So light that's coming in kind of in a straight line will bend, but will bend in different amounts based on the color. And that has to do with frequency and wavelength, which my oldest kid is 6, so I didn't really want to get into that. But that's what's going on, is it's bending in different amounts. And depending on how much detail you want to get into, we did talk about the reason it bends because it actually slows down. Now, Einstein figured out that light always goes the same speed. It always goes the speed of light, which is 300 million meters per second, or 300 million meters per second, or 186,000 miles per second. Again, I happen to have that up here, but that would be totally fine for a teacher or a parent to say, I think it goes really fast. Let's ask Google. But anyway, it goes really fast. And it always travels at a constant speed, but when it goes through a medium like glass or water, it will actually get absorbed and re-emitted, absorbed and re-emitted, and that changes its speed. And sometimes the example I use is if you're driving down the road and your tires are on nice, smooth asphalt, and then the right side of your car goes into something not as smooth like dirt or grass, your car is going to steer to the right as it goes from, as part of the car is in a medium that slows it down and causes it to steer. Light does something similar. But the effect of going from one medium to another is more for the purple end of the spectrum. Okay, so we talked about that. We saw rainbows go around the house. And then we decided, so that's dispersion. Another place you see dispersion is actual rainbows. So a great way to make a rainbow, if you don't happen to have one up in the sky right now, is to go out in the yard and turn your hose setting on mist and just spray a mist into the air. And what's happening, again, is dispersion, but it's a pretty cool phenomenon that if the sun is behind you, sunlight passes over your head, enters the tiny water droplets, bounces in the water droplets, and comes back into your eyeball. So the light you're seeing is actually sunlight coming from behind, bouncing inside a tiny droplet of water, and then coming back into your eye. But that bouncing happens at an angle that is specific to the color of the light. And so the bounce happens at a slightly shallower or steeper or smaller angle for like purple, and it's a little bit bigger angle for red, and again you get dispersion. So that was 2 different examples of dispersion. Any kind of prism that you have around the house or rainbows, water droplets, those are 2 different ways you can get dispersion to happen. Fun fact, rainbows aren't actually bows, they're perfect circles, but they're usually partially cut off by the atmosphere, or by the horizon. If you look on Google, you can usually find rain circles, pictures taken by spacecraft or airplanes or something like that, where you can actually see the entire circle. Kind of fun. Okay, before we finish, we wanted to look at, I think we did 2 other types of rainbow type of experiments. The first one was just go grab a CD or a DVD somewhere in the house. I know those are getting older. I'm not sure my kids even knew what a DVD was, but actually my 4-year-old was quite familiar and fond of CDs. And we were able to shine light onto the CD and see that creates a rainbow. And again, kind of cool permutation of that is if you're using incandescent light, so if you're using either the sun itself or some kind of incandescent light, the kind of light that just gets really hot and glows in your house, that will create a rainbow effect on the CD. And what's going on there is slightly different. It's kind of cool. The tiny little grooves in the CD cause light that's entering the reflective surface of the CD to bounce off at very slight difference of height. Now, and by the time it gets to your eye, it's had to travel a very slight difference in path length to your eyeball. And what happens is the waves actually interfere with each other because there's a slight difference in distance. And so I didn't want to get too into it with my kids, but I was able to sort of explain to them that if you have 2 waves like this and they go on top of each other, they add, but if they are opposite, they could cancel out. And so that's what actually happens is you get destructive interference with CDs. So you get waves coming out and running into each other and canceling each other out. It's basically as deep as I got it. Also really cool, if you have nowadays we have LED lights, and LED lights aren't this nice broad spectrum of color. They usually are just emitting a few discrete frequencies, and sometimes you can actually see the difference if you have an LED light and an incandescent light on a CD. Okay, the last thing we did was, it was a nice day, so we went outside and blew soap bubbles. I didn't have the bubble formula stuff around, so what we did is we took a cookie sheet, filled it with water and not baking soda, water and dish soap, thanks. And then took a metal coat hanger, bent it into a circle, and we were able to make bubbles pretty easily. Again, this is something that back when I started teaching, I might have like experimented for hours ahead of time to get just the right mixture of soap and just the right size of coat hanger. But I wanted my kids to see that this is just a big experiment. So it took us a few tries to get it right, get the concentration right, and get the coat hanger bent right. But we were eventually able to make some really nice bubbles. And of course, when you make a soap bubble, you get to see those cool patterns. Those cool patterns are also coming from destructive interference. When light goes into this, hits the soap bubble, some of the light bounces off the outer surface of the soap bubble. Some of the light passes just one bubble thickness in and then bounces off the back surface and comes back out. So you're getting light just kind of like the CD, just a very, very tiny length difference when it hits your eye based on the thickness of the soap bubble, and you're getting destructive interference. And if you look closely, because of gravity, the soap bubbles are usually thinner at the top and thicker at the bottom as the water kind of falls down. And so you're getting the fatter or redder wavelengths canceled at the bottom and the thinner wavelengths canceled at the top. And at the very top, sometimes it's so thin you're getting complete destructive interference and you'll get bands of black, which is kind of cool. So anyway, we blew soap bubbles and we kind of experimented and talked about rainbows by looking at those. I think that was it. Yeah, and so that ended up being like probably a couple hours just running around the house trying to find things that make rainbows and kind of investigating light and playing with it. And we had a lot of fun. Thanks. I don't know how I forgot this, but I forgot to mention one last activity we did. And the activity was geared toward this. When students or kids tend to draw rainbows, or maybe adults when they think of rainbows, they think of these discrete bands of color. So you get your red crayon out and draw the red, then you get your orange crayon out and draw the orange. But in reality, a rainbow is an infinite spectrum of colors. And so that was another continuum, or spectrum was another vocab lesson for the day. What we did is I actually, once they were done drawing their rainbows with crayons, I took the crayons they chose, the red, orange, yellow, green, blue, purple, and I taped them to a piece of wax paper and said, look, here is a rainbow made of discrete colors. Then I took a hair dryer and then melted it all together. It wasn't the beautiful, like perfect rainbow I was kind of expecting, but we did get to see the colors blend together. And with kind of aiming the wind just right, I was able to get kind of what I was shooting for, and that is a continuum or a spectrum of colors. And so hopefully that drove home the point. And it's just kind of fun to watch crayons melt. It's kind of cool. And the last thing, we talked about ways that we're going to improve some of the experiments that we had done that day. And the plan is, I haven't tried this yet, but I do remember seeing this on YouTube. I think you can use 2 sticks with string to make your big bubbles. So rather than a rigid hoop made by the coat hanger, I think we're going to try the string technique where you dip string into the soap and then make a hoop and you can run it around. I don't know if anyone has any ideas. Shoot me an email, text me a comment, I don't know, something like that. But anyway, we're always looking for ways to improve our experiments. Thanks.